Leo's Tech Talk. Video 16. Rise of high-throughput Wi-Fi. How 802.11n or Wi-Fi 4 changed everything. Few people realize that the Wi-Fi we enjoy every day can be traced back to one standard, the one that shattered the 54 megabits per second barrier, and ushered in the era of true high-speed wireless, IEEE 802.11n, better known today as Wi-Fi 4. If you've ever streamed HD videos, joined video calls without constant buffering, or transferred large files over Wi-Fi, chances are you have 802.11n to thank for it. In this video, we're going to explore the innovations that completely transformed wireless networking and laid the foundation for every modern Wi-Fi standard that followed. The IEEE officially ratified 802.11n in 2009, and it represented the biggest leap in Wi-Fi technology since wireless networking began. Compared to earlier standards, like 802.11b, 802.11a, and 802.11g, 802.11n delivered dramatically higher speeds, wider coverage, improved reliability and a much better user experience. Because of these improvements, 802.11n is often referred to as high throughput, or simply HT. So, what made it so revolutionary? Let's explore. MIMO. The biggest breakthrough introduced by 802.11n was MIMO, which stands for multiple input multiple output. Earlier Wi-Fi standards relied on a single antenna to transmit and receive data. 802.11n changed that completely by allowing multiple antennas on both the transmitter and receiver. Instead of sending all the data through a single antenna, MIMO allows several antennas to transmit different portions of the data simultaneously. This technique dramatically increases throughput while also improving reliability, especially in environments where signals reflect off walls, furniture, and other objects. MIMO turned what was once considered a problem, multipath reflections, into an advantage. Spatial streams. MIMO gives us multiple antennas, but antennas alone don't increase speed. The real speed boost comes from something called spatial streams. A spatial stream is an independent stream of data transmitted over the wireless channel. Think of a highway. If you only have one lane, only one stream of traffic can move at a time. But if you expand the highway to 2, 3, or 4 lanes, several vehicles can travel side by side. Spatial streams work in exactly the same way. Each stream carries different pieces of data simultaneously, allowing much higher overall throughput. For example, a 2x2 MIMO device can support up to 2 spatial streams, while a 4x4 MIMO device can support up to 4 spatial streams, provided both the transmitter and receiver support them. This is one of the key reasons 802.11n was able to achieve such a dramatic increase in speed. Channel bonding. Another major innovation introduced by 802.11n was channel bonding. Previous Wi-Fi standards used a 20 MHz channel. 802.11n introduced the ability to combine 2 adjacent 20 MHz channels into a single 40 MHz channel. By effectively doubling the available channel bandwidth, the standard could carry significantly more data under suitable radio conditions. Think of it like expanding a 2-lane road into a 4-lane highway. More traffic can flow at the same time. Higher data rates. When you combine MIMO, spatial streams, and 40 MHz channel bonding, the result is a massive increase in performance. 802.11n supports theoretical data rates of up to 600 megabits per second, using 4 spatial streams with a 40 MHz channel. Compared to the 54 megabits per second maximum offered by 802.11a and 802.11g, this was a tremendous leap forward. For the first time, Wi-Fi became fast enough to comfortably handle HD video streaming, online gaming and large file transfers. Dual band operation. 802.11n also introduced another important improvement. It could operate in both the 2.4 GHz and the 5 GHz frequency bands. This gave manufacturers and users greater flexibility. The 2.4 GHz band provided better coverage and longer range. The 5 GHz band offered cleaner spectrum with less interference and higher performance. Users could now choose the band that best suited their environment. Frame aggregation. Another clever optimization was frame aggregation. Normally, every packet transmitted over Wi-Fi includes protocol overhead. When sending many small packets, that overhead becomes inefficient. 802.11n solved this by combining multiple MAC frames into a single transmission. Instead of sending numerous small packets individually, the access point sends them together as one larger transmission. This makes much better use of the available airtime and significantly improves overall throughput. Beamforming. 802.11n also introduced beamforming. Traditionally, Wi-Fi signals are transmitted equally in all directions. Beamforming changes that. It allows the access point to steer RF energy towards a specific client device, instead of broadcasting it uniformly. By concentrating the wireless energy where it's actually needed, beamforming improves signal strength, increases reliability and often extends usable range. Block acknowledgement. Another improvement came through block acknowledgement, commonly known as block ACK. In earlier Wi-Fi standards, every transmitted frame required its own acknowledgement. That meant a lot of additional overhead. 802.11n introduced the ability to acknowledge an entire block of frames using a single acknowledgement. This significantly reduces protocol overhead and improves transmission efficiency. Backward compatibility. One of the reasons 802.11n became so widely adopted was its excellent backward compatibility. New 802.11n access points continued supporting older 802.11a, 802.11b, and 802.11g devices. This allowed users to upgrade their wireless networks without replacing every existing device overnight. The transition to faster Wi-Fi became much smoother and far more affordable. Guard interval. One final enhancement worth mentioning is the guard interval, often abbreviated as GI. The guard interval is a small pause inserted between transmitted symbols to reduce interference caused by delayed signal reflections. 802.11n supports two guard interval options: long guard interval 800 nanoseconds and short guard interval 400 nanoseconds. Using the shorter guard interval reduces idle time between symbols and can increase throughput by roughly 11%, provided the wireless environment has minimal multipath interference. It's a small change, but one that contributes to the impressive performance of 802.11n. Security. Security also received an important upgrade. 802.11n made WPA2 the mandatory security standard. It also supported WPA and WPA2 Enterprise using 802.1x authentication, providing much stronger protection for both home and enterprise networks. Although WEP remained available for backward compatibility, it had already been proven insecure and was strongly discouraged. Recap. 802.11n completely changed the Wi-Fi landscape. It introduced MIMO, spatial streams, channel bonding, dual band operation, frame aggregation, beamforming, block acknowledgement, stronger security, and numerous PHY layer optimizations that pushed wireless networking into an entirely new era. With theoretical speeds reaching 600 megabits per second, dramatically improved coverage, and much greater reliability, Wi-Fi was no longer just a convenient alternative to Ethernet. It became the primary way people connected to the internet. In many ways, every modern Wi-Fi standard that followed, including Wi-Fi 5, Wi-Fi 6 and Wi-Fi 7, were built upon the foundation established by 802.11n. And here's a question for you. Which feature of 802.11n do you think had the biggest impact on modern Wi-Fi? Was it MIMO? Channel bonding? Beamforming? Or perhaps something else? Let me know in the comments. In our next video, we'll uncover the exact technical innovations that allowed Wi-Fi to leap from 54 megabits per second to an astonishing 600 megabits per second.